Here are some instructions to help you with lab atmospheric moisture, pressure, and wind. Here are the activities and the lab report questions that I'm assigning, and this particular video is going to cover activities 1A to 7, and of course skipping the ones that are not assigned. So activity 1 has to do with the change of state of water, and throughout this lab you really want to focus on reading the paragraphs at the beginning of each activity, such as this section right here. There's a lot of information in this lab that you're going to want to go through and highlight and notice keywords, and I'm going to do some of that with you for some of the more complex sections. This one I think is fairly straightforward. What you're going to do is you're going to look at this diagram and you're going to put in the places that say process one of the choices from up here. There are a few questions on the next page. Question 3 in particular I want you to pay attention to because it asks you about the concept of absorbing or releasing heat. And when it comes to understanding the weather, this is an important factor that drives certain kinds of storms. So for example, if we look down here at the liquid water, and you can picture this as the ocean, when that water turns into gas, okay, and I'm not going to tell you the process because you have to figure that out, but it absorbs energy. And when that gas returns back to rain, when it becomes from water vapor to rain like in a hurricane, it releases energy, and that energy actually heats up the storm, which gives it more energy and drives it. So these are important concepts for understanding severe weather. I did not assign activity 1B, so let's move on to activity 2. Now activity 2 again has this opening paragraph with a ton of information. So I might suggest that you pause the video right now, read these 3 paragraphs under activity 2, and then maybe put the video back on and see how I go through this paragraph, because I'm going to go through it pretty slowly. First of all, water vapor, the very first word in this section. Make sure you understand that water vapor is a gas and it's invisible. Many people think of water as liquid water, but water vapor, when it has that word at the end, means it's an invisible gas. Okay, so water vapor is in the air, but we can't see it. And there's a little cartoon over here showing some things. And one of them is this container that has dry air above water. So no water vapor in that air. And then they show evaporation occurring where little water molecules are in the air. And they're just showing them here for a visual effect. But we can't see this. This is an invisible thing up here. How do we know there's water vapor up there? Well, it turns out that water vapor, once it's up here in this area, starts bouncing around and creates some pressure. It's called vapor pressure. And so we can measure the change in pressure from here to here and say, oh, there must be some of that invisible water vapor bouncing around. Okay, so back here to the second paragraph, humidity is a general term for the amount of water vapor in the air. Sometimes it's called water vapor content. Again, it's invisible, so it has to be measured with an instrument. There are different ways to talk about humidity, and 3 of them that are in this lab are mixing ratio, relative humidity, and dew point temperature, and I'm going to get to those in just a moment. But before we get to those concepts, we want to make sure you understand the concept of saturation. The idea behind saturation is that the air can only hold so much water vapor, and then it can't hold any more. And when we get beyond the point where it can't hold any more, it actually rains, and so we'll get to that eventually. So saturated air is air that cannot hold any more of this invisible water vapor. So this cartoon here is showing the dry air, and then here they have some evaporation of the water occurring. And because there's some water vapor pressure in here, it sometimes bounces water molecules back into the liquid form. And so there's just kind of this process of evaporation and condensation, but the air is not saturated. There's, as it says in this little text here, there's more water evaporating than condensing. Eventually, though, the air becomes saturated, and you've got all the water vapor that it could possibly hold. And down here in this description, there's the concept of water vapor. They say that saturated air is when the water vapor molecules returning to the surface balance the number leaving. So basically, you're in an equilibrium state where no more water vapor can be put into the atmosphere. I like to think of an analogy of a sponge when it comes to saturated air. So you've got your dry sponge, You add a little bit of water to that sponge and the sponge will absorb it, but the sponge is not going to leak any water because it's not saturated yet. Once the sponge is saturated, you've got all the water it could possibly hold, then if you add any more water, it's going to drip out of the sponge. Okay, so that's the kind of concept here. So some terms that I want to emphasize here are mixing ratio, and that is how much actual water vapor is in the air. The saturation mixing ratio, which is how much water vapor would saturate the air. So if I jump back, the mixing ratio would be, how much is here. The saturation mixing ratio would be here. That's how much it can hold at the most. And that saturation mixing ratio is temperature dependent. And that's really important when it comes to understanding various processes in the weather. So there's a table here, Activity 2's table, and it's giving you a bunch of different temperatures in centigrade or Fahrenheit, and then the saturation mixing ratio, or how much water can that air hold at that temperature. It's given in grams per kilogram, which is kind of an odd set of units, but basically it's saying that, let's say for example, at 50 degrees Fahrenheit, the air will be saturated if it has 7 grams of water per kilogram of air. And so a kilogram, you might remember, is a mass, really, but it's also equivalent to a liter volume. So think of a liter of air, and there are 7 grams of invisible water vapor bopping around. That air is saturated. At 77 degrees, where it's warmer, the same liter of air could actually hold 20 grams of water vapor. And so that's what it means to say it's temperature dependent. So relative humidity tells us how much water vapor is in the air relative to how much it could hold, relative to its saturated amount. And so there's an equation here that's actually on your page with Activity 3, which we're not there yet, we're Activity 2 still, but I've repeated it up here, it's a little bit fuzzy. The idea is relative humidity is the mixing ratio, okay, so another term that we talked about, the water vapor in the air, divided by the saturation mixing ratio, which is the maximum it could hold, times 100. So for example, in 50-degree air, the water vapor content is 3.5 grams per kilogram. What's the relative humidity? So you go to this chart and you look at 50-degree air, this is Fahrenheit, and you see that it can hold 7 grams of water vapor per kilogram. So you use this formula, the mixing ratio is 3.5, that's how much is there. The saturation mixing ratio is from this table, how much could be in the air, and you use the formula and you find out that the relative humidity is 50%. The air has 50% of the water vapor it could hold before it is saturated. Okay, so that's a lot of explanation for Activity 2, and we really haven't even started it yet. The first thing that you are asked to do is to prepare a graph on this page that graphs some of the points in this table so you can visually see what this table is showing you. So I'm going to do this with you for some of the points, and you could either use the temperatures in centigrade, which is this column, or the temperatures in Fahrenheit, which is this column, and then the saturation mixing ratio is all on the y-axis. I'm going to use the centigrade because they're a little bit more evenly distributed. They go by 10s and 5s. So at minus 40 degrees centigrade, which actually is also the same as minus 40 degrees Fahrenheit, that's the one place where those two temperature scales overlap, the saturation mixing ratio is 0.1. Well, on this graph from 1 to 10, 0.1 is pretty much at 0. We go to the negative 30, and 0.3 is just about at the same point. Negative 20, we're at 0.75, so we're still less than 1. Finally, at negative 10 degrees centigrade, we go up to 2, so we're going a little bit higher. Then at 0 degrees, we get to 3.5. And now it goes every 5 degrees on the centigrade scale over here instead of every 10. So at 5 degrees centigrade, we have a mixing ratio of 5. So I've got my little dot here halfway between 0 and 10, and that's 5. And so now it's going to be easier. I'll let you do the rest of these. Okay? And then you're going to answer some questions about this. The first question here says, how many grams of water vapor are required to saturate a kilogram of air at these various temperatures? At 40 degrees centigrade, how many grams of water vapor are going to saturate a kilogram of air? So you go back to the table, you look for 40 degrees centigrade, which is here, and you see that it takes 47 grams of water vapor to saturate the air. So that one's 47. So those questions there, you're just going to look at the table. And then there are some more questions here that you can think about. I'm not going to go through everything for you, but that should have gotten you a good start for activity 2. Moving on to activity 3, now we're focusing more on this relative humidity equation that I already went through. The first question says, given these air temperatures and these water vapor contents, what is the relative humidity? So remember, water vapor content is the mixing ratio. It's the number that goes on top. The bottom saturation mixing ratio you figure out from the table based on the temperature. So let's do that. 15 degrees centigrade, 10 grams per kilogram is the most it could hold, and that's what's going to go on the bottom. So I've got 2 grams per kilogram on the top divided by 10 times 100 is 20%. So the relative humidity in this case is 20%. Now you're going to repeat this for some other water vapor contents that will go in the top. But we're always at 15 degrees, so you're always going to have 10 grams per kilogram as the saturation mixing ratio. And now that you've completed this section, what kind of trends do you see when you add or remove water vapor, when water vapor is increased or decreased? Then question 3 uses this same approach of calculating relative humidity, but this time you're going to do it at different temperatures with the same water vapor content, and then it's going to ask you for trends you see there. So that's going to be pretty similar to what we just did. Now 5 and 6 are what I call superstar questions because they take all of this stuff that we're learning and they put it into reality, right? You're probably thinking, why do I need to know this? Well, for number 5, many homes are heated in the winter. What effect does heating have on the relative humidity inside the home, and what can be done to lessen this effect? 6, explain why the air in a cool basement is relatively humid or damp in the summer. So these are things that will get you thinking based on temperature change and relative humidity. And then number 7 is just a summary. 3B is shown here. It's a very short one. And if you read again the very beginning, you'll see that this has to do with a misconception that relative humidity is an accurate indication of the actual quantity of water vapor in the air. And so they go through this activity here to kind of show you what they're talking about. Now, what you have here is similar information to activity 3A, but in a slightly different order. You're given the relative humidity. You're given this number here. And you can figure out the saturation mixing ratio from the chart. What they want to know is the mixing ratio. They want to know this value here. So you know that the relative humidity is 40%. You don't know what the mixing ratio is. And then I found the saturation mixing ratio of 20 at 77 degrees from the chart. And then you do the math. 0.4 equals this number over 20. And so multiply both sides by 20 and you get 8. So the water vapor content in this particular situation at 77 degrees, 40% relative humidity, is 8. So then you go ahead and do the same thing for the winter one, and then you'll be able to think about what this misconception is about. Okay, so number 4, activity 4 is very short. It just has 2 questions. Again, you want to read up here about dew point temperature, and it is the temperature at which air is completely saturated. So looking at table 2 again, the same table we've been looking at, determine the dew point temperature of a kilogram of air that contains 7 grams of water. So basically it's asking you at what temperature is the saturation mixing ratio 7 grams. Okay, so I'll let you guys work on those on your own, and we can always talk about this in class if you're stuck. 5 we're not doing, 6 we're not doing, but I do want you to read this section up here about dew point and condensation. So if air is cooled below the dew point temperature, the water vapor condenses. So far I've been talking about how water vapor, invisible, accumulates in the air, and then there's a saturation value where it can't hold any more. So what happens if you put in more water vapor, or what happens if you lower the temperature? What happens is that water vapor condenses to liquid, and that's usually in the form of rain or dew or frost if it's below freezing. This is an important concept right here. We're not going to do the activity related to it. So here we are at the last activity that this video is going to help you with, and this has to do with thinking about how the daily temperature and the relative humidity are related to each other. Again, I encourage you to read this paragraph, underline, circle things that you have questions about, write questions in the margin. And let's just look at this chart here. So we have 6 a.m. to midnight, and then another 6 hours on day 2. And then in the y-axis we have temperature, which is in this red curve. So what you can see is it's coldest on day 1 at 6 a.m. and it gets warmer and warmer and warmer till about, usually the warmest temperature of a day is not necessarily noon, it's more like 3 or 4 in the afternoon. And then the temperature drops and it goes down, 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 down. On this y-axis we have relative humidity, and relative humidity is shown in this dashed line. So relative humidity in this particular case starts very high at day 1 at 6 a.m. It drops down and then it goes up again. So most of these questions are about just those two curves. On which day and at what time is the relative humidity the highest? So you're looking at the relative humidity line. On which day and time is the temperature the lowest? Again, you're looking at the temperature line. And then the lowest relative humidity. Write a general statement between temperature and relative humidity. So I'll give you a little hint. Would you say that relative humidity and temperature are directly related? Meaning one variable goes up and the other variable goes up, or one variable goes down and the other one goes down? Or would you say they're inversely related, where one variable goes up and the other one goes down? So those are kind of your two options. And then the last question has to do with this dark blue line, which is the dew point temperature. So this is the air temperature in red, and the dew point temperature is below it. And remember that if the air temperature drops below the dew point temperature, then your air is 100% saturated, relative humidity is 100%, and you're going to condense liquid or solid water, frost or dew. So that was your quick and dirty overview of the first half of this lab, and it should provide some good foundation for the second half of the lab.